Welcome to Gradient Canvas. Today we're going to learn about embeddings, how a computer turns the meaning of a word into a point in space, and why that one idea powers search, chatbots, and every large language model. Here are two sentences. How do I fix a punctured bicycle tire? And repairing a flat bike tire. You understood instantly that these are the same question, but look at the actual letters. They share almost no words. Punctured isn't flat. Bicycle isn't bike. Tire isn't even spelled like tire. So any program that matches words would say these two have nothing to do with each other. And yet every search engine, every chatbot, every retrieval system finds one from the other in milliseconds. There's a single idea that makes that possible, and it's one of the most quietly beautiful ideas in machine learning: turn meaning into geometry. Let's try the obvious thing first. A computer can't read letters, so give every word in the vocabulary a number. Cat is 17, dog is 4002, car is 900. Now, is cat closer to dog or to car? Well, 17 is closer to 900 than to 4000, so by these numbers a cat is more like a car than like a dog. That's obviously nonsense. The numbers are just filing cabinet labels. The distance between them is an accident of alphabetical order. So people tried to be more careful, give each word its own dimension, a vector that's all zeros with a single one in that word slot. This is called one-hot encoding, and it's honest. It no longer pretends cat is nearer to car. But look at what it does say. Take any two of these vectors and compare them, and you get the same answer every single time, totally unrelated. Cat and dog, unrelated. Cat and car, unrelated. Every word sits the exact same distance from every other word. On the corner of an enormous cube with one dimension for every word in the language. We removed the wrong answer, but we're left with no answer at all. What we actually want is a space where distance means something. So let's do it by hand just to see what we're aiming for. Forget the vocabulary list. I'll make a map with two axes I choose myself. Left to right, how alive is this thing? Bottom to top, how big is it? Now place a few words. Cat, very alive, quite small. Dog, very alive, a bit bigger, so it lands right next to the cat. Car, not alive at all, fairly big, way over on the other side. Truck, not alive, even bigger, right beside the car. And look what happened. I never told this map that cats and dogs are related. But because they scored similarly on the things that matter, they ended up as neighbors. Meaning became position. That is the entire idea of an embedding. Of course, nobody handpicks axes like aliveness. There are far too many shades of meaning, and most of them we couldn't name if we tried. So here's the trick that replaced the handwork, and it's one line from a linguist in 1957. You shall know a word by the company it keeps. Look at the sentences these words actually appear in. The blank curled up on the sofa. I fed the blank this morning. Cat fits, dog fits, car does not. Words that show up in the same slots, surrounded by the same neighbors, must be playing similar roles, so we should give them similar vectors. And notice what that buys us. Nobody has to label anything. The raw text of the internet already contains all the evidence. One small note. A real model does this for tokens, the little chunks that words get split into, but the idea is identical. Turning that into training is delightfully sneaky. Give every word a vector of random numbers, pure noise, no meaning at all. Then set up a game, hide a word and make the model guess it from its neighbors. It guesses badly at first. Every time it's wrong, we nudge the vectors, pull the word a little closer to the words that surround it, and push it away from random words that don't. Do that a few billion times across a mountain of text and something remarkable happens. Nobody ever asked this model to organize meaning. All it did was try to predict missing words, but the only way to win that game is to arrange the vectors so that similar words sit together, so the geometry appears as a side effect. The prediction was the excuse, the map was the prize. Now, if meaning is position, we need to measure nearness, and there's a subtlety worth getting right. We don't usually use straight line distance. We use the angle between the two vectors through something called cosine similarity. Take the dot product, then divide by both lengths. Let's actually do 1. Cat is 9, 2. Dog is 9, 3. The dot product is 9 times 9 plus 2 times 3, 87. Cat's length is the square root of 85, about 9.2. Dog's is the root of 90, about 9.5. Divide 87 over about 87 and a half, 0.99. Almost perfectly aligned. Now cat against car at 1 and 7. Dot product, 9 plus 14, 23. Divide by the lengths, 0.35. Same calculation, wildly different answer. And why the angle rather than the distance? Because a vector's length mostly tracks how common or how emphatic a word is, while its direction is what carries the meaning. Cosine ignores the loudness and listens to the content. Here's where it stops being merely useful and starts being uncanny. It's not just positions that mean something, directions do too. On this little map, walking from man to woman is one particular step, 4 to the right. Now go and stand on king and take that exact same step. You land on queen, which we can write as pure arithmetic. King minus man plus woman equals queen. This model was never taught what royalty is or what gender is, but because those distinctions show up consistently in how the words are used, they became consistent directions in the space. And once a concept is a direction, you can do algebra on meaning. Now, one piece of honesty, because this is the most oversold result in the field. With real embeddings, it's far messier. The answer usually only comes out as queen because the search deliberately excludes the 3 words you put in, and plenty of analogies simply fail. The deep idea is real. Concepts live along directions. The party trick is fragile. Now everything so far has one serious flaw. We gave each word one vector, but consider, I sat on the riverbank, and I wired the money to my bank. Same 4 letters, 2 unrelated meanings, and a single vector has to be some hopeless average of both, a point stranded between rivers and finance, close to neither. This is exactly what modern language models fixed. Instead of one fixed vector per word, they compute a fresh vector every time, built from the actual sentence it's sitting in. The mechanism is called attention, and it's a video of its own. The result is that bank near river and bank near money come out as 2 genuinely different points. The word stopped having a meaning and started having a meaning in context, which is, of course, how language actually works. And once you accept that meaning can be a point in space, the idea escapes language entirely. A whole sentence can be one point, so can a paragraph, a document, a photograph, an audio clip, a snippet of code, a product, a user. And here's the striking part. You can train 2 different encoders to put their outputs into the same space so that a photograph of a dog and the words "a dog" land in nearly the same spot. That's how you search a photo library by typing, or find a song by describing it. Which finally answers the question we opened with. To search by meaning, you embed every document once, ahead of time, and store the points. When a question arrives, you embed the question the same way, and then you simply look for the nearest points, not the matching words, the nearest points. Our 2 bicycle sentences share no vocabulary at all, but they're asking the same thing, so they were placed in the same neighborhood, and a nearest neighbor search walks straight from one to the other. This is the retrieval in retrieval augmented generation. It's how a chatbot answers from your company's documents without ever being retrained on them. Find the nearest chunks, paste them into the prompt, and let the model read. Every recommendation feed, every duplicate detector, every related article strip is this same move. 4 warnings before you go. First, and most practically, embeddings are only meaningful relative to the model that made them. 2 different models produce 2 unrelated coordinate systems, so comparing a vector from one against a vector from another is pure gibberish, and if you re-embed with a new model, you have to rebuild the entire index. Second, close does not mean true. The vaccine is safe and the vaccine is not safe sit almost on top of each other because they're about the same topic. Similarity is not agreement, and a retriever will happily hand you a confidently contradictory passage. Third, these vectors learn whatever the text contained, including its prejudices, the very same arithmetic that gives you queen also reproduces occupational stereotypes, and that lands in every system built on top. And fourth, watch the units. Cosine assumes you have divided by the lengths. Skip that normalization and long common vectors quietly dominate your results. So, embeddings in one breath. A one-hot vector says that every word is equally unrelated to every other. An embedding replaces that with a point in a few hundred dimensions, learned by trying to predict the words around it, so that things used alike end up placed alike. Nearness is measured by angle. Directions carry concepts. Context reshapes the point. And once meaning is geometry, what does this mean becomes, what is near it? A question a computer can answer instantly. One last thing worth knowing. This isn't a separate tool bolted onto language models. It is their very first layer. Before a transformer does anything clever at all, it turns each token into exactly this kind of vector, and then attention starts moving those vectors around based on what's nearby, which is precisely where we'll go next. Thanks for watching. This is Gradient Canvas, where we make AI beautiful and understandable. If you enjoyed this and want to understand AI concepts, please like, subscribe, and share it with others. Join us to explore more AI concepts from neural networks to transformers. See you in the next video.